All right, welcome back to the second episode in our general chemistry series. This is lecture number 2 on units, measurements, and significant figures. So, if you recall from our last lecture, we focused primarily on the first part of chapter 1. That was the fundamentals of chemistry and the some of the fundamental laws and kind of our ways of classifying matter and energy. And if you haven't viewed that yet, if you have not seen that video yet, I encourage you to go back to lecture number 1 and to do just that. Go back and look at it. For today, we are looking at expanding our concepts and starting to look at how we measure things, how we look at things, how we conduct general kinds of experimentation, how we express numbers and values. And so this is all about units and measurements today, and the way that we conduct and measure our numbers and do calculations with them. The next lecture in this series, lecture number 3, will be all about unit conversions, where we will take those calculations and start to do something meaningful with them, and start applying significant figures in other kinds of ways other than just simply measuring how many significant figures there are in a given value. So let's start with units. Now, there are lots of different unit systems out there. You're probably most familiar with the what is called in the world of science the customary system of units. That's where we measure things like feet and inches, miles, fluid ounces, pounds, pints, quarts, gallons, and so on. It's a system that most of you have grown up in. You're probably also familiar, at least in some part, in some way, with the metric system. The metric system where we use all of those prefixes and we talk about things in terms like centimeters and millimeters and liters and kilograms and that kind of thing. Now, closely related to that system is something called the international system, or the SI system. And the primary reason why the metric system or the international system has such acclaim is that there's a wide amount of consistency in their measurements. When I go from one unitary system to another, there's a common language that is spoken. The prefixes are all the same. All of the units are spaced apart by a factor of 10, which makes their conversion extremely easy compared to if I want to figure out how many feet are in a mile. Well, I know that the conversion is 5,280 feet per mile. But if I want to convert that feet into inches, I then have to multiply that by 12. And if I want to convert it into something else, is a different value that I'm going to have to multiply by. There are 2 pints in a quart. There are 4 quarts in a gallon. So there isn't a whole lot of consistency. One unit system isn't easily derived into the next unit system. And that's one of the big problems with the customary system. The metric system in the US, or excuse me, the SI system, are comprised on these ideas of these prefixes and also on the concept of what is called a base unit. So in total, there are 6 base units in the SI system. Now, why do we call these base units? Because these are the units that all other units are derived from. So a unit that is singular in that sense is a base unit. We cannot devise that unit from other units. Whereas something like volume is considered a derived unit. The reason it's considered a derived unit is it is derived from the base unit of length or distance. I can find the volume of an object by taking the length times the width times the height, and that would give me 3 measurements of distance that I could multiply together to give me a measurement of volume. So our base units fall into this kind of line. And there are 6 of them in total. There's actually a 7th one, but we're not going to really talk about it. The 7th one is the luminous intensity, the candela. Really, the only place you're going to see candelas is for things like, you go to buy a light bulb. Light bulbs will give you a measurement of luminous intensity in terms of candelas, tell you how bright the light is. Other than that, these are our primary base units. And so for mass, our base unit is the kilogram. The base unit for distance or length is the meter. The base unit for temperature is Kelvin. More about that in a little bit. The base unit for time is the second. The base unit for electrical current is the ampere or the amp. We won't touch on that one too much until Gen Chem 2, Chem 106. The quantity of a substance is the mole. We'll talk about that one a lot this semester, especially toward the end. The other thing that we know about the base unit system, about the SI system, is that we have common prefixes that are associated with each of these base units and the derived units that come from them. Now, these prefixes correspond to numerical values that relate that prefix to the base unit. But there are a number of these prefix units here that we just simply do not need to know. And so where I tell us to really focus our information, really focus our study, is what we're going to put in this red box right here, from 10 to the 9th to 10 to the negative 12th, giga to pico. That is the box, that is the area in which you really need to focus. You need to know what these prefixes mean. Now, some of these prefixes are a little bit less important than others. Very rare that you see deca or hecto or even deci for that matter. You don't see those 3 very often, but it's important to know what they mean. When it comes to the exponentials and the values here, remind yourself that these values are relative to the base unit. So what that means is that 1 giga is equal to 1 billion base units. And 1 deci is equal to 0.1 base units. Important to know, because probably one of the most common mistakes that is made by students in doing unit conversions is improperly adjusting for a metric conversion. So doing things like multiplying by 1,000,000 when you should divide by 1,000,000. Those kinds of things. So understand that these exponentials, these numerical values, apply to the base unit when you're doing a conversion. So there are 10 to the 9th meters in a gigameter. There is 10 to the negative 12th meters in a picometer. And if you can keep that straight, that will certainly go a long way toward helping you meet your goals and do things correctly. So let's talk a little bit about temperature then. We made mention of it on the base units. We talked about how the base unit for the temperature scale is the Kelvin scale. Now, what is temperature? Temperature is a measurement of heat quantity. In particular, we're looking at how much kinetic energy the molecules of a substance have. The higher the temperature is, the more kinetic energy those things have, the more they are going to vibrate, move around, and generally just be active. The lower the temperature is, the less of that quality exists. Now, the 2 scales that we are probably the most familiar with are these 2 right here, the Fahrenheit scale and the Celsius scale. Those two are probably the ones that we have the most familiarity with. We've seen in weather forecasts, we've seen in other places, Celsius and Fahrenheit both being used. They're both based upon what is called a relative definition. So Fahrenheit was all about making thermometers that included liquids that would expand or contract based upon temperature changes. So you heat up a mercury thermometer, the mercury inside expands and it goes further up into the glass tube. It cools down, it contracts, it comes down in the tube as well. Celsius works off of a similar kind of concept, but systematically defines the freezing point of water at 0 and the boiling point of water at 100. Fahrenheit, by the same token, does similar things with Fahrenheit at 32 and 212 for the freezing point and boiling point as well. Problem with both of these scales is they are considered relative scales. That is, they are based upon a definition that has no true grounding in energy in this case. That definition that they are based upon is the freezing point of water and the boiling point of water. Now, this is different from Kelvin. The Kelvin scale is what we call an absolute scale. The absolute scale for the Kelvin scale is based solely on molecular energy. And this, of course, means that at the 0 point, molecules would have no energy and would not be moving. And that's what we refer to as absolute 0. So the reason why the Kelvin scale is so favored has everything to do with this last fact. It's an absolute scale. We get an absolute definition of energy related to the temperature scale itself. So the kind of go-to example I use for this is along the lines of, let's say that you wake up tomorrow and it's 20 degrees Fahrenheit outside. And you wake up the next day and it's 40 degrees Fahrenheit outside. Now, both, by most accounts, would be considered cold days. But would it really, if I was comparing 20 degrees Fahrenheit and 40 degrees Fahrenheit, would I say that the 40-degree day is really twice as hot as the 20-degree day? No. Relative to each other, they're both cold. They're relative to your body temperature, they're both cold. And if I look at the energy of the molecules at 20 Fahrenheit and the energy of the molecules at 40 Fahrenheit, they don't have a linear relationship to each other. At least not a one-to-one relationship. The molecules at 40 degrees are definitely not moving twice as fast as the ones at 20 degrees. But on an absolute scale like the Kelvin scale, that is absolutely true. When I see differences in scale, when I see differences in value of temperature, that directly means that they are going to have differences in terms of their temperature as well. Differences in terms of something noticeable and tangible in terms of their energy. 40 degrees Kelvin is twice as energetic as 20 degrees Kelvin. The molecules are literally moving twice as fast. They have twice as much energy. So there is a difference there. And that's why the Kelvin scale is favored among the two. Now, if I compare these to each other, you can see I've got my three graphs here, Fahrenheit, Celsius in the middle, and Kelvin on the far right. We can see that for the most part, there is a relationship between the two. But what I really want to point out to you is look closely at Celsius versus Fahrenheit. I'm going to point out those defined points there. You can see that for the boiling point of water and the melting point or freezing point of water. On the Kelvin scale, they are 100 degrees apart. On the Celsius scale, they are 100 degrees apart. On the Fahrenheit scale, they are 180 degrees apart. So I've got a difference of 180 on the Fahrenheit scale, 100 on the Celsius scale, and 100 on the Kelvin scale. So really the only thing that's separating the Celsius scale from the Kelvin scale is the fact that the Celsius scale seems to be shifted upwards by a few degrees. In fact, it seems to be shifted upward by 273 degrees. And so when I look at that definition, when I look at that conversion between the two, I will see that to get Kelvin from Celsius, which Celsius is usually the way that we will measure temperature, I just take that Celsius temperature and I add 273 to it. Now, where does this other equation come from? This 5/9 times Fahrenheit minus 32. Well, this is a really common way of showing this particular equation. I actually favor a different way, though. If I can write it out another way, Celsius is equal to Fahrenheit minus 32 divided by 1.8. From a scalar standpoint, this equation that I just wrote and the equation that is written here mean the same thing, would give you the exact same results. Why do I favor this equation? Because it's not a fraction. 1.8 is a lot easier to enter into your calculator than 5/9 or 9/5. Where does that 5/9 or 9/5 come from? Well, it comes from the relationship between the Celsius and the Fahrenheit scales. A 100-degree difference in Celsius is a 180-degree difference in Fahrenheit. If I break that down into lowest terms, 18 degrees for every 10 or 9 degrees for every 5. Or 1.8 degrees Fahrenheit for every 1 degree Celsius. So that's where the 1.8 comes from. Now, the nice thing about this particular equation is that when we rearrange it, we can do so very easily. 1.8 degrees Celsius times degrees Celsius plus 32 would give me that Fahrenheit. So again, I tend to favor this form of the equation just because the decimal value is a lot easier to work with than the fraction value. But that's how I can convert between the scales themselves and do so relatively simply, relatively easily. Let's do an example problem. Now, for this example problem, I invite you to pause the video and try to work it out on your own. Go ahead and construct your answer, unpause the video, and you can watch me do the problem from top to bottom and see how you did. So the temperature of coffee from the student union is found to be 205.43 degrees Fahrenheit. First of all, if you're ever served coffee that hot, let it sit for a while. That'll scald the inside of your mouth real good. Second of all, you're asked to find out what the temperature is on the Celsius and the Kelvin scales. So go ahead and hit pause right now. Try to work out that problem on your own, and then come back in a couple of seconds and after you've worked the problem and see how you did. So we're told the Fahrenheit temperature of 205.43 degrees Fahrenheit. We want to convert this into Celsius and into Kelvin. Now, remembering our equations, to get Celsius, we would take Fahrenheit minus 32 over 1.8. And to get Kelvin, we would take Celsius plus 273.15. So with that in mind, we just need to plug in the right values in the right places. So for Celsius, Celsius is equal to Fahrenheit 205.43 minus 32 divided by 1.8. So following the math here, we have 205.43 minus 32 and so that would be 205.43 minus 32 would be 173.43. We're going to take that and divide it by 1.8. And if I do that, I get 96.35 degrees Celsius. So that's part one. In part two, I need to convert the Celsius into Kelvin. So Kelvin is equal to Celsius 96.35 plus 273.15. Kelvin temperature would be 369.50 Kelvin. Now, notice that for Kelvin, the unit there is not degrees Kelvin, it is just Kelvin. So you do not need the degree sign or anything like that. You can just go straight up with the Kelvin there. So that's this kind of problem. And you'll see more examples of these in some of your post-lecture materials and certainly in your chapter 1 homework. Let's move on though and talk about measurement. Now when it comes to measurement, every unit system out there has certain defined values associated with them. The SI system is no different. There are specific things that make up the definition for what a meter is, what a second is, what a what you name it. There are specific values that are defined for those, and those are all evaluated in terms of giving us a consistent value so that we're all talking about the same thing, and they're usually known with some level of precision. When we don't have precision, or when we don't have absolute precision, where we know something exactly, what we call that is uncertainty. And there's always going to be uncertainty present in anything that we measure. There is no such thing as an exact measurement. Let me say that again. There is no such thing as an exact measurement. Every measurement that we take comes with some degree of uncertainty present in it. Now, there are some exceptions to the rule. For example, counted values are known to be exact. If you count the fingers on your hand, you're not going to come up with an imprecise number. You will count them and you'll get exactly a whole number of some sort. The other kind of place where we see exactitude is if I'm converting from one unit system to another. There are occasions where there are some defined values. So for example, 1 inch is equal to 2.54 centimeters. That is an exact conversion. There are 60 seconds in 1 minute. That is an exact conversion. There's no ambiguity there. There's no there's nothing there that would lead you astray otherwise. So there are some values that we can say that are exact, but they're relatively rare. Anything that we have to measure is going to have some level of uncertainty to it. So even if I measure something in centimeters and then want to convert it into inches, yes, the conversion between centimeters and inches is exact, but the measurement of the original measurement of centimeters or of inches will have some uncertainty associated with it. So we cannot escape uncertainty when we are measuring things. So with that in mind, another practice problem to consider, again, pause the video here if you want to try to work these out for yourself before getting the answers. I'll go ahead and let you stop. And so of these three things, which are exact values and which ones are uncertain values? Well, again, anything that we can count is an exact value. So if some poor soul climbs up the stairs of the Washington Monument and counts that there are 893 steps, that would be an exact value because it would be counted. Now we have to trust that they counted it correctly, but it would still be an exact value, even if it's imprecise, even if it's incorrect, rather, inaccurate. For the second one, the width of the Golden Gate Bridge at 27.4 meters, this is a measured value, so it's going to be uncertain. The level of uncertainty depends a lot on what you use. So if I'm measuring something at 27.4 meters, there's a good chance I don't have a very precise instrument. And so there's going to be a good bit of uncertainty associated with that measurement. It could realistically be anywhere between 27.5 and 27.3 meters. And that would be a good solid what, 20 centimeters either way, 10 centimeters either way. So not super precise there. The third one, a gold nugget has a mass of 3.4590 grams. Now, this level of precision, 4 decimal places, that sounds really, really great. Understand, this is still a measured value. Now, our level of certainty in terms of the mass of that gold nugget is far more certain than our measurement of how wide the Golden Gate Bridge is. But they both have uncertainty associated with them. Just because you are uncertain doesn't mean that you have doubt necessarily about the value in terms of its accuracy. Obviously, the more precision that you can measure with, the more you can trust the number. So the point that we're trying to hammer home here is that every measurement that you take has some degree of uncertainty associated with it. Depends primarily on what instrument you use to make that measurement. The more precise the instrument is, the less uncertain the uncertain value is in terms of how well we can trust the number and that the number is what we say it is. The uncertain digit is one of estimation. And so the last recorded digit on any measurement is your uncertain digit. It is estimated. Now, in electronic balances, that means that the last value that the balance gives you. When you use something like a ruler or a tape measure, you will be responsible for creating that last uncertain digit. Because you'll have to estimate, okay, where is it between those two marks? And how far away is it from one mark versus the other? So there is some uncertainty that is going to be associated with every single measurement. Now, the primary difference here, if I look at these balances versus these ones, and we have both of these kinds of balances in our labs, this one gives us an uncertain digit in the 1/100ths place. So 1/100th of a gram uncertainty, which isn't too bad, all things considered. versus 1/10,000th of a gram of uncertainty. Well, this is pretty darn precise. Doesn't necessarily mean that it's more accurate, but its level of precision, its uncertainty is shrunk down to the point where we are a lot more confident that that value is right around that value. Whereas here, there's a little bit more uncertainty because of the decimal place that's being recorded. Two terms that often get confused are precision and accuracy. Now, precision itself is based upon two ideas. One of them, reproducibility. How well, if I measure something on a balance, how reproducible is that result? That's precision. And to that end, we can usually express precision of that kind by citing a range between high values and low values. So I take an object like this pen, I measure it on a balance several times, record all the measurements, and see what kind of range that I get. And the highest value and the lowest value, we subtract those from each other, and that gives us a tolerance, a range. So that's what this plus minus refers to. This is something called a tolerance. The general rule of thumb is that the smaller the value of the tolerance is, the more precise the measurement is. So that's kind of the second value associated with precision. And that is, not only is it reproducible, but how many decimal places can I get? How close, how tight is that tolerance range? The wider the tolerance range, the less precise we consider the instrument, the less trustworthy we consider its measurements. Accuracy, on the other hand, is all about closeness to the true value. So if I have an object that weighs 25 grams, accuracy would be how well does that balance tell me how close to 25 grams I am. And so we can run into those kinds of things with accuracy. Now, just because an object is accurate in measurement doesn't necessarily mean it's precise, and vice versa. Of the two types of error, it is far better to be precise but not accurate than accurate but not precise. If you have a good precision but bad accuracy, you can usually account for that. That's called a systematic error. And you can usually reprogram the balance or account in some kind of way for a systematic error. So if your balance consistently says that it's 5 grams higher than it actually is, over time you can learn to recognize that particular difference and adjust for it by making sure that all of your measurements get subtracted by 5 before they're recorded. That's a systematic error. Far more random errors, ones where we have, poor precision, generally lead to poor accuracy as well. And those are the kinds of things that we want to avoid because we really can't account for them. That's when we start to get into, maybe it's time to replace this balance. Maybe it's time to replace this thermometer. It's no longer reading accurately. It's no longer reading precisely. We just got to get rid of it. Now, when it comes to accuracy, there are a number of means of checking accuracy. We call those means calibration. So usually that means taking some kind of known material and using it to determine how well how accurate an object is in terms of its ability to measure things. The last topic for today is one about significant figures. Now, significant figures are one of those things that we kind of hammer you on here in general chemistry and in other sciences as well, because it's important. We don't want to get caught overestimating and overindulging some of the errors that are associated with measurements. When we attach good significant figure rules, we can gain confidence in measured values. So take, for example, I've got an object I weigh on two different balances. First balance says that the object weighs 3.59 grams. The second object says that it weighs, or the second balance says the object weighs 3.5882 grams. Now, both seem to be saying close to the same thing. In fact, if I round the second balance up to the same number of decimal places as the first balance, I would get the same value. Which one of those do we trust more? Well, it'd be the second balance because it's got more decimal places. It's got more overall instrumental precision. I have more significant figures in that second balance. And so that increases my confidence. That tells me, okay, that's probably more close to accurate in terms of what the actual mass is. So the more significant figures that our measurements have, the general confidence, certainty that is associated with those measurements increases. But we can't just simply invent significant figures in order to increase confidence. We will always be limited by the object, the instrument itself. So how do we go about evaluating how many significant figures a particular balance or a particular measurement tool gives us? Well, there are some guidelines that can help us. Most of the guidelines regarding significant figures fall around this general idea. The general idea is that when I have a measured value, non-zero numbers are significant, and zeros are the things that we have to watch out for. What kinds of things do we have to watch out for with regard to zeros? Well, first of all, if a zero is starting a number, those zeros at the beginning of a number are never significant. What we call those zeros are placeholder zeros. And they do things like tell us that our measurement here is a really small number, 0.000000559 meters. Okay, that's a really small number. That's 5.59 micrometers or microns. Small. If I don't have those zeros there, this number takes on a whole different meaning. 5.59 microns is way different than 0.559 meters. One is thinner than a piece of paper. The other one is about, about 1.5 feet in length. Very different from each other. So placeholder zeros like this, their only purpose is to hold the place, to make it so that we are showing the correct value of the number. They don't contribute to significant figures whatsoever. When we have zeros after a non-zero number, they tend to be significant, with the one notable exception. So if I have a decimal point, let's take this value again, 0.0000059. If at the end of that, I had a couple of zeros, that would be significant. This is showing additional precision of the instrument compared to this one. So kind of the same kind of thing that we saw in the previous slide. In This example, I had 3 significant figures. In this one, I have 5. But what if I don't have a decimal point? What if I have a number like this? $121,000 grams. Well, it's really difficult to know whether or not those are significant or not. Our general rule of thumb is that if we don't see a decimal point, zeros like these would be placeholder zeros as well. It would not be significant. We would say that this particular measured value had 3 significant figures, just these 3 right here. 1, 2, 3. Problem is that's not always the case. Sometimes those zeros are significant, sometimes they are not. This is when it is best to use your scientific notation, because scientific notation will always show the correct precision, because every digit in scientific notation is a significant digit. Important thing to know. Make sure that you've got that written down somewhere. Every digit in scientific notation is a significant digit, which means that you need to handle those properly. So if I wanted to express this number with having 4 significant digits, I would need to make that adjustment accordingly in my scientific notation. It would be 1.210 times 10 to the 5th grams in that case. That would show 4 significant digits because my scientific notation always shows the correct number of significant figures. In that case, 4. Finally, if we have zeros between non-zero numbers, they're significant. So again, the only zeros that we have to worry about are the ones that either begin a number and are never significant, or the ones that end a number, and depending upon the circumstances, whether there's a decimal point, whether the scientific notation is present or not, those may or may not be significant. Again, scientific notation really helps to clarify that significance. Now, what if I have to do calculations? Well, the general rules for calculations with significant figures are that how you handle them really depends on what kinds of mathematical operations that you're doing. But before we get into those specifically, there are some general guidelines I'd like to give you. First of all, when it comes to rounding in calculations, try your best not to do so until the very end. Limit the number of times you have to round a number. Because every time that you round a number off, you're introducing a little bit of error. So if let's say that you had a 4-step calculation, and every step along the way, you're rounding off the number, rounding it off. Well, in those 4 steps, you're doing 4 different roundings. You're going to end up with far different answer, at least most of the time, than this person who does all 4 of the calculations in a row and then rounds at the very end. Which one of you are correct? Well, the person that did it all in one calculation step actually has the more accurate result. Every time you round, you introduce error. Introducing error makes your results a little bit less accurate, a little bit less trustworthy. Second guideline, there's what we call the weakest link principle. And what the weakest link principle says is that when it comes to rounding, you're going to use the measurement that has the fewest decimal places or significant digits when you do that rounding. The other guideline here that you'll want to add is something that we call the rule of fives. If the number next to the last significant digit is 5 or greater, you're going to round up. If not, if that number is less than 5, then you round down. Really simple. I mean, this is the kind of rounding discussion that you've probably had since upper elementary school. 5s and up, round up. 4s and down, round down. So hopefully shouldn't be that complicated for you as you're doing those calculations. Now let's look at these two here. When it comes to mathematical operations, there are two sets of rules. One that abides when we are adding and subtracting, one that abides when we are multiplying and dividing. So for adding and subtracting, here's where decimal place matters the most. When we are doing any kind of rounding, we want to pay attention to decimal place when we add and subtract. So the easiest way to show this, I've got an example here, 10.011 plus 11.01. If I put it into my calculator says that the sum of those two is 21.021. Now, based upon what I added together, I can see that this 1 here at the end was an uncertain digit in the first measurement, and this 2 was an uncertain digit in the second addend. Our weakest link principle tells us that we are going to round to the value that is the leftmost decimal place that has an uncertain digit in it. That would be this 2. So using our rule of 5, 1 is less than 5, we're going to round down. 21.02 is our answer. In our second example, and then, again, this is where things get a little bit more complex. 19,900 minus 375. On the surface, if you were following this from a math problem perspective, you would look at this and say, okay, I just subtract the two values, 19,525 is my answer. Problem is, we have to assume that these are measured values. And as measured values, significant figure rules apply. Since these two zeros are ambiguous, we have to make the safest assumption, and that safest assumption is that they are non-significant, which means that the last significant digit was that 9 in the 100ths place, as opposed to this 5 in the ones place. Our weakest link principle says we need to round to the leftmost uncertain place. That 2 means we're going to round down. So that's where we get 19,500. Now, the other thing to make note of here, we cannot lose sight of the values themselves. And what I mean by that is this. I've seen it happen on a number of occasions where a student does something like this and correctly identifies that those zeros are insignificant and mistakes it for meaning that they are not real. And so instead of giving me an answer of 19,500, they give me an answer like 195, where they just completely chop off those last two values. That's not what happens. Now, if we want to avoid ambiguity, the best thing that we should do here is convert that into scientific notation so that there is no discussion, there is no issue there. 1.95 times 10 to the fourth would be the correct scientific notation. That way we can be certain there are only 3 significant figures there, as opposed to 4 or 5. So adding and subtracting, in my mind, that's the harder one, because decimal places are a lot more difficult to keep track of in general. When multiplying and dividing, it's a little bit easier, because all we need to keep track of are the number of significant figures. So in this example, I have 3 significant figures in 9.19. I have 4 significant figures in 3.171. I have 2 significant figures in 1.0. That 0 is significant because it follows a decimal place after a decimal point after a non-zero number. I look at my 3 measured values. The weakest link principle says that I go with the one that has the fewest significant figures, which means even though my calculator juts out 29.14149, I round that to 2 significant digits. That gives me a total of 2. 29 is the correct answer there. So again, multiplying and dividing, far more simple than adding and subtracting. In terms of getting the correct number of significant figures. Now, it's going to feel weird at first to basically chop off a whole bunch of numbers. But just because your calculator generates them doesn't mean that they're significant. You have to use your brain, you have to use your guidelines to generate and make sure that you are determining which numbers are significant, which ones are estimated, and which ones don't matter. And so in this case, 29 is the correct answer. 9 is the estimated digit. Everything else after that really doesn't matter at all. All right, we'll end with one last final example, just as a review problem. I've got 3 measurements for 3 different nails here. What I want to do is this. We're going to do 2 problems here. What is the total mass of the 3 nails? And I'm also going to throw in what is the average mass of the 3 nails. So again, go ahead and hit pause here. Try to do this one on your own. Come back in a couple of seconds and I will work out the problem. You can kind of check yourself against me and see how you did. All right, so in doing this problem, we're going to find the total mass, I'm going to need to take those 3 masses and add them together. If I do that, 13.47 plus 13.43 plus 13.4653, I end up with a total mass, according to my calculator, of 40.3653 grams. Now, before I go ahead and click that one into my homework, I would want to look at it and say, did I do my significant figures properly? And so, since I am adding here, I need to look at where do those numbers come from. And so I can see that nail 1 and nail 2 are both known to 2 decimal places, whereas nail 3 is known to the 4th decimal place. Keeping with my weakest link principle, I'm going to round that 6 either up or down. Since 5 is next to it, I'm going to round it up. And so my value here is actually going to be 40.37 grams. That is going to be what I record as the total mass of those 3 nails. Now, that sounds kind of absurd. After all, that is less, or excuse me, that is more than what the calculator said those 3 values were. But what this is accounting for is that there is uncertainty in those first 2 nails that was not there in the 3rd nail. And so to account for that uncertainty, I have to include that second digit, and that ends up meaning I have to round it up as a result. Now, to do the average mass, remember, average is just the total mass divided by 3. If I take that total mass and divide by 3, my calculator spits out 13.4551. What of that do I keep? Well, this is a division. You may look at this and say, well, I need to divide by 3. Or I'm sorry, I need to have one significant figure because my value 3 here only has one significant digit. Well, remember, this value is exact. There were exactly 3 nails that we added here. Exact numbers do not factor into significant figures. So what I really need to do here is the number of significant figures that I kept at the beginning come out at the end. So 1, 2, 3, 4. This 5 is the last significant digit. I'm going to look and see that the 5 next to it is going to cause me to round up. And so the average mass is going to be 13.46 grams. So that's all for this particular lecture. As I said before, if you have questions about this concept or about any of the items from this, bring those with you to our next lecture, or reach out to me on Remind or an email and ask me a quick question. From there, we will get into using these rules and units to do conversions, and that will be the subject of lecture number 3. So until then, I'll see you in class. Have a good day.